Okay, hi everyone. We want to continue our discussion about quicksort, and if this is the first time you see quicksort, and congratulations, and quicksort is one of the hardest algorithm to implement and to analyze. When I was learning this course when I was a student, so this is a hard topic. And especially later, when we analyze the quicksort, we are going to see a lot of the mathematical equations, and probably you don't like that. And to be honest, I'm not a big fan of that too. But anyhow, let's do a very quick review on what's the idea about the quicksort. So quicksort is a sort in place algorithm. So that's one of the things we love. And another thing is, well, usually if we talk about the time complexity, it sorts O n log n in average case. But in the worst case, it will be O n square. So worst case O n square, not impressive, right? But well, with some smart implementation, and usually we can avoid having this worst case, so the worst case won't happen very often. But anyhow, later in this class we are going to talk about how we can avoid having the worst case happen again and again and again. Okay, so for the quicksort, and remember we start to talk about the partition. So to do the partition, we have to have a pivot, and after we have the pivot value, and then we want to partition all the values in the unsorted list into two parts. So on the left half and the right half, and then for the left half, those are the values smaller or equal to the pivot, and on the right half, we have the values greater or equal to the pivot. And for those two halves, and we just call them two subarrays, and they may, well, the partition may not really be 50%, 50%. Sometimes we are lucky, we have some, a kind of balanced partition. In some cases, and we could have 1 to n minus 1, or even 0 to n. So that's possible. And for the quicksort implementation, and we specify three parameters. A is the list we want to sort, and P is the left bound, and then R is the right bound. So the implementation is, as long as the left bound is still smaller than the right bound. So if this condition is true, this means at least there are two values in this sublist to be sorted. And otherwise, if P is equals the R, and then this means there's only one value in the sublist, and then we don't have to do anything because this sublist has only one value, nothing to be sorted. Or a sublist with one value is already sorted. Okay, and then if this condition is true, we want to do a partition. And after we have the partition will return us the index of the pivot. And after we have the pivot, and then we want to do two recursive calls, and one recursion we want to do the quicksort on the left half, and another one we want to do on the right half. But you have to pay attention to one thing. Okay, so in the line on the line 3, we have the quicksort A, and then the left bound, and then Q minus 1. So that is, we want to sort the left half, but we are not touching the pivot. Okay, and then for the line 4, we sort A and then Q plus 1. So the pivot plus 1, and then to the R, which is the right boundary. But anyhow, in those two recursive calls, we don't touch the pivot anymore. The pivot will stay there forever. Okay, and well, as you may see, well, a lot of things actually happen in the partition, right? So for the partition, we want to separate those values into two parts or two subarrays, and then the pivot, it will sit in the middle. And for the partition, if we want to describe the process in words, and then we want to grab the first value, the very first value of the list to be the pivot, and then we will have the pivot stay at the very beginning for now, and then we want to have two cursors, an I and J. For those two cursors, they're in charge of finding a pair of the values. They are both on the wrong side. So for the I, which is the left cursor, we want to find a value which is greater or equal to greater than the pivot. And then for the right cursor, we want to find a value smaller than the pivot. Okay, those two values, they are on the wrong side, so we want to swap them. And then we continue. And when do we stop? Well, if I is greater or equal to j, and this means those two cursors, they have already met, and then we can say, oh, we want to stop, because even though those two cursors may still be able to find two values, greater than the pivot, smaller than the pivot, but we want to make sure that the I cursor is lower than the J cursor, and otherwise they have already met, and then we want to stop this kind of swapping. Okay, so let's see the real implementation in this case. Well, to do a quicksort, and we for the quicksort function call, and we only call that with one parameter, which is the list to be sorted. So, and how do we sort that? And then we want to create a helper function. So for this helper function, we can take a list, and then also the lower bound and the upper bound of this the part of the list to be sorted. So for this quicksort helper, and the first call will be the list, and then start from the very beginning, which is the index 0. And by the way, this is the implementation in Python. And so we start from the 0, the lower bound, which is index 0, and the upper bound, which is the length minus 1. So we want to sort the whole list. Okay, and then for the quicksort helper, and then we send a list, and then the first and the last, which are the lower and the higher bounds of the range to be sorted. Okay, and then if first is smaller than the last, and then we want to do a partition. And for the partition, we are trying to we are returning the index of the pivot, and we call that the split point. And after that, we want to do two recursive calls, and then for the pivot, we don't touch it anymore, and we just sort the lower half and the upper half of the values. Okay, and then we have the implementation of the pivot. So for the pivot, we want to grab the pivot value, and then as you can see, we are using the first index the value on the first index to be the pivot value. And then for the left mark, which is the I cursor, we started from the first plus 1. So, well, that's where we start the I cursor. And for the right mark, which is the J cursor, as we discussed before, and that will be the index of the last. And we are going to start this search process. And after we find one value, one large value using the left mark, and then one small value using the right mark, and then if we want to check if the right mark is still smaller than the left mark, and if it is true, and if the right mark is already smaller than the left mark, and then we will say it is already done, because those two cursors, they have already met. And otherwise, we want to swap the values on the left mark and the right mark. So we swap them. And eventually, after we have done this while loop, we want to swap the first value, which is where the pivot was at, with the right mark. And then eventually, we want to return the right mark, which is the new location or the new index of the pivot. Okay, so this is the partition part. And I have a couple questions. So what is the running time of the partition? So what is our goal? Our goal is we want to scan all those values, and then we want to swap them if we find a pair of the values they are on the wrong side, and eventually we want to put the pivot in the middle. So when we are visiting those values, and it's important to remember, we are touching those values once, right? So if we have a list of n values, and we are going to use I cursor or J cursor, but we are visiting them once. So it doesn't matter, we only touch them once. But but why am I saying what is the busy or active case? Well, this depends on how many swaps we want to do. So if we want to execute this line a lot, and then, well, this means there are many values on the wrong side, so we have to do a lot of swaps. Or if there are, for most of the values or for all the values, they are on the right side, and then well, before those two cursors meet, and then there's nothing to be swapped, that will be an idle or inactive case. So, but my argument is, it doesn't matter. For the algorithm of the partition, it is a big theta n time algorithm anyhow. It doesn't matter we do a lot of the swappings or there's no swapping to be done at all. But remember, we only touch all the values once and only once, and that's enough. And so this partition is a linear algorithm, and we can see for the busy cases, and then it could be 5n, and for the idle cases it could be 3n, but it doesn't matter. It is a linear time algorithm. Okay, so well, the next part we want to talk about how do we analyze the quicksort. And for the just now we say for the partition is linear and we don't have to worry about the best case and the worst case. But for the quicksort, we do. So what do I mean? Well, if we have a good partition, and why it is good? So if you have good partition, a 50-50 partition, and then we are, instead of fighting against a big problem to sort a big list, now we can sort, our goal will be we sort two smaller lists, and then for both of the subproblems, the size will be roughly half of the original problem. So this will be a good thing. And what's the opposite? The opposite will be, say, if we pick a pivot, and this pivot value is either super large or super small, and what will happen? So, well, if we pick a super large or super small pivot, and then in the extreme case, all the values will be on one side of the pivot, right? So if the pivot is the maximum of the values to be sorted, and then, well, all the remaining of the values will be on the left half. And then we have what kind of partition? We have, okay, so let me draw you this. Say we have a list of the values, and then if we are unlucky, we pick the max to be the pivot. And then for the partition, what are we going to have? We are going to have the max to be the pivot. And then for all the remaining values, they will be on the left side, and then there's really nothing on the right side. So for this partition, what have we done? Is that really a divide and conquer? The answer is probably no, because we didn't really have a chance to divide this problem into two sub-problems, because on one side there's nothing to be sorted and all the remaining values are on the other side. And even though we are using the idea of the divide and conquer, but in this case this is a failed divide and conquer. Okay, and what is the best case? So for the best case, well, this is almost cheating. Say we are lucky, and then we are able to find the median of the list to be sorted right at the very first value. And what will happen? So we are going to have the median in the middle as a pivot. And then we have roughly half of the value on one side. So half of the values on one side, and then we have half of the value on the other side. And then this is definitely the divide and conquer we love, because, well, the median will simply stay here, and then we have already put this we have already divided this big problem into two smaller problems to be solved. So how do we sort the lower half of the values, and how do we sort the upper half of those values, and then we just put them together, and then we have the entire list to be sorted. Okay, so this is definitely the best case. And for this one, this is a failed divide and conquer, because, okay, the max unfortunately is a median, but, well, in the final sorted list, it's actually the very last value. Because why? Well, on the right half, there's no value there, and then all the values are on the left side. So is that a divide and conquer? I wouldn't call that. It's more like getting one step closer to the final goal, right? So this will be the worst case. Okay, so well, this is the idea of the possible best case and the worst case, not for the partition, but for the quicksort. Okay, remember for the partition, it doesn't matter. It doesn't matter. It is a busy case. We have a lot of swaps to be done, or it is an idle case. There's no swapping at all. The partition itself is a linear algorithm. However, partition is only part of the quicksort, and for the quicksort, we have the worst case and we have the best cases. Okay, so let me pause the video here, and I will continue in the next video.